Hello, welcome to this week's Naked Scientists, which is a science phone-in extravaganza for you, with me, Chris Smith, and also with our specialist panel, who I will introduce you to now. So the lineup today: Dominic Ford is an astrophysicist from Cambridge University. He has an appreciation for heavenly bodies, haven't we all? Hi, Dominic.
Hi there, Chris.
Also, Laura Howes is a chemist. She also writes about science for the Royal Society of Chemistry's Chemistry World magazine. Hi, Laura.
Hi there, Chris.
So she's looking forward to reacting to your questions as they come in. Ginny Smith is also with us. She is a chemist and a psychologist, so she's going to be getting her head around all of your questions. Hi, Ginny.
Hi there.
And good old Dave Ansell, who's an experimental physicist who likes to do the experiment to find out what's going on. He's also here. Previous exploits include building a chocolate teapot to prove that one really isn't useless, earning him a place on the Wikipedia teapot page. Well done, Dave. And also doing the experiment to find out how fat you would have to be to stop a bullet with your belly. But you didn't do it with a human, did you, Dave?
We did it with a big bucket of jelly, because unfortunately they wouldn't let us do it with people.
Thank God for that. So if you have any questions, they're ready and waiting to answer them for you. Already in the lineup this week, why water makes different noises just before it boils. We'll find out the answer to that one. Whether a person sitting in a bath of water can still dehydrate. And can magnets on a water pipe stop them furring up? What are the answers to all of those? Also, we've got a question for you to get your head around. Can you tell us, this is a trivial, tricky question, how can you throw something as hard as you can and have it come back to you even if it doesn't hit anything and there's nothing attached to it and no one catches it? Any questions or the answer to that one? 08459 25 2000 is the telephone number. Email chris@thenakedscientists.com, tweet @nakedscientists, or find us on our Facebook page. It's The Naked Scientists, and let's go straight out of the blocks with a call from Akim. Hello, Akim.
Hello, how are you?
Very well, thank you. How can we help you?
I've always been wondering about the sound of water. Boiling water obviously bubbles and it's loud. Cold water is quiet. You don't hear a whisper out of it. But when you heat water, it also makes a sound. And it gets louder the more you heat it. The thing that I was always surprised about is that it seems to be loudest just before it boils, and then gets a bit quieter when it goes to the bubbling, boiling noise. Why is that? What is the sound of heating the water?
So this is all to do with, if you think about what's happening before it actually boils properly. The heating element is over 100 degrees centigrade, therefore the water around it is going to be producing steam even quite early on when it's starting to boil. And these bubbles are created, and then if it's not quite boiling yet, they move up into a cooler area of water and they cool down. If a steam bubble cools down very quickly, it suddenly wants to disappear and it collapses and it forms a cavity. If you imagine this bubble kind of collapsing symmetrically around each other, it kind of slaps into itself. And this is known as cavitation, and it's very, very noisy, and it's actually quite a destructive process. You get this in boat propellers, and if the boat propeller goes too fast, you actually get little bubbles of steam which collapse again and actually completely smash up the surface of the propellers, and you can see horribly eaten up propellers. So therefore, going back to the kettle, as it heats up, slowly these bubbles are getting bigger and bigger and bigger, and they're collapsing harder and harder and harder until eventually they get hot enough that they get all the way up to the surface and they just pop gently.
So the reason it gets louder just before the water boils is because that's when the bubbles are at their biggest to start with, and therefore they've got the biggest collapsing to do.
So it's the biggest bubbles which are collapsing, and then they get to the point where they reach the surface, at which point they just pop gently and it gets much quieter.
Dave, thank you. Akim, does that sort that one out for you?
That's a fabulous explanation. Thank you very much.
Thanks for joining us on the programme. You're listening to a special question and answer edition of The Naked Scientists with me, Chris Smith, as well as Laura Howes, Dominic Ford, Ginny Smith and Dave Ansell. If you'd like to send any questions, you can do so to chris@thenakedscientists.com. You can follow us on Twitter @nakedscientists, or you can look us up on Facebook, facebook.com/thenakedscientists. Laura, this one looks like it's good for you. Daniel says on Facebook, facebook.com/thenakedscientists, the molar mass of ozone, in other words, how much a certain quantity of ozone weighs, is just under 48 grams. The molar mass of oxygen, which is O2, it's one atom fewer than ozone, is 32. So how does the ozone layer, which effectively must weigh more than the oxygen in the atmosphere, stay above the planet and not go tumbling back down to Earth? He says he finds that very perplexing.
It's a really good question, Chris. Obviously, the ozone layer is really important because it protects us from UV rays, but actually that's one of the reasons why it actually is up there, because it's continually being reformed. It needs to be up there, getting the UV rays, absorbing them, having that chemistry going on in the atmosphere. So it is actually sort of heavier, but actually it's because it's continually being reformed.
I guess another factor here is that because the ozone layer is absorbing all this ultraviolet radiation from the sun, it's actually getting really quite hot. We think of temperatures decreasing with altitude, but when you get up to these quite high altitudes, that air is getting hotter. And, of course, hot air floats because it's less dense. That's how a hot air balloon flies. And so this ozone is naturally quite buoyant because it's hot.
Dominic, thank you. Ginny, this one looks promising for you. Brian Beck has got in touch to say... very much been enjoying the programme, but he wants to know what vertigo is. He says, ever since the age of 18, I've dealt with vertigo at least once a year, sometimes 2 or 3 times, and sometimes the doctor has done to prescribe something called Antivert, which is an anti-sickness medication for it. But what's going on with me? He plaintively asks.
So vertigo is this sensation of dizziness or spinning, and most people will have experienced it, if not any other time, when you've had a few too many drinks. But some people get it quite regularly, and it's all to do with your inner ear. So inside your ear, you have 3 semicircular canals, little sort of loopy things, which are filled with fluid. And they're all at 90 degrees to each other, and that's how you know which way up your head is and which way it's moving, because the fluid inside them moves, knocks into these little sensor hairs, and that tells you how you're moving. When you spin around, the fluid in them starts to spin as well. But after you stop, it keeps spinning for a while. And that's what makes you feel dizzy after you've been spinning around. But lots of things can make you feel like you're moving even when you aren't, which is what is happening in vertigo. There's some circumstances when it can be caused by little pieces of debris that have found their way into the inner ear, and they confuse the signals that are being sent to the brain. That type of vertigo tends to happen only when your head's in a certain angle, so the debris is hitting the little cells. It can also be linked with migraines, in which case the problem's probably actually not in your ear, but in the nerves or in the brain itself. But scientists still don't really understand migraines. They're a bit of a mystery to us.
Do you know what is weird, though? Why the body has evolved to make the decision that when you get motion sickness or vertigo or something, to throw up. I mean, what's the point of that?
Well, vomiting is a sensible response if you've eaten something bad. And it seems that dizziness can sometimes be an indicator of poison. So I think that's how that evolved, that in some circumstances it was very useful to throw up because you'd eaten something bad. And actually, if you throw up a few more times than you need to, that's better than not throwing up when you should.
Suppose so, although the person whose car it is might disagree. You're listening to The Naked Scientist with Chris Smith, with Dave Ansell, with Ginny Smith, Laura Howes and Dominic Ford, a huge assemblage of big brains here to answer your science questions for you this week. If you'd like to send one in, chris@thenakedscientist.com is the email address. You can also tweet at Naked Scientist or submit them onto our Facebook page. John's got a question for you, Dominic. Hello, John.
Hello. Basically, what it was, I was just wondering what happened to photons emitted from the sun when they hit the air. And I was wondering if they actually increased the mass of the earth at all.
Yes, in a sense I think they do, because you're probably familiar with Einstein's really famous equation E equals mc squared, which is this sort of iconic equation of relativity. And what that's saying is that energy has some mass associated with it. It's a very tiny mass. But when you're looking at really large amounts of energy, like the power that the sun is delivering to the Earth every day, then that starts to become quite an appreciable mass. And I actually sat down half an hour ago and was doing this calculation, and I think it's about 7 kilograms of energy that the sun delivers to the Earth every second. But if you're then asking, is the energy of the Earth increasing as a result of that? Well, the Earth's energy is not actually increasing as a result of the radiation from the sun, because if it was, it would be getting hotter. And we know that the Earth's climate has been fairly steady for millions of years. So what that means is that the Earth is radiating to space just about the same amount of energy as it's receiving every day from the sun. It's in this thermal balance.
Though they're having a couple of NASA missions recently which have been actually attempting to measure that, because if global warming is happening and the Earth is warming up, then the Earth should be re-emitting less energy than it's absorbing. And they reckon it was less than a watt per square metre is sort of disappearing somewhere into the Earth. So some of that energy should be increasing the mass of the Earth very slightly just by heating it up.
Oh, that's great.
Thank you very much for joining us, John. I hope that answers the question.
It does, yeah, that's very good. Thank you.
Okay, so there's a modest, if any, weight gain owing to the sun putting energy into the Earth through, as Dominic says, E equals mc squared. Great to have you with us, John. Thank you. Don't forget our little quizette we're running for you. We would like you to tell us, and I'll read this to make sure I'm being fair, how can you throw something as hard as you can and have it come back to you, even if it doesn't hit anything, there's nothing attached to it, and no one else can catch it? Can you tell us? Email chris@thenakedscientist.com. Pinchas is on the phone. Hello.
Good evening. How are you all?
I'm very well, thank you. I think you have something you would like to ask Laura.
It's very well known that heat rises. So if I heat water, the hottest point of the water should be at the top. Why then, when I freeze water, does it freeze from the top down?
So this is a really brilliant question. It's all about how weird water is as a substance. Water, if you think about it, you know that ice floats. That's why your ice in your drink floats to the top. It's why we can ice skate on rivers, although make sure the ice is fairly solid first.
Good job you can ice skate on rivers rather than
having to go down to the bottom. And I think probably the wildlife and the fish in the bottom of the lakes are quite like that as well. It's all to do with the way that hydrogen bonds. So water bonds, and it forms these things called hydrogen bonds. So you've got the oxygen in the middle of the water and then these two hydrogens coming off of it. And so you're right that as you heat water up, it becomes less dense and it floats. But then at about 4 degrees, there's this wonderful sort of turning point. And actually, as you're cooling it down, it gets denser and denser. And then these hydrogen bonds come into play and it starts to make this structure, making it less dense. So that's when the cold water floats to the top and then eventually freezes.
So it's sort of almost starting to freeze in little lumps and then unfreezing. So more and more of it is in the sort of ice structure, so it's bigger than it should be. So it starts to expand as it gets colder, which is really, really strange.
Yeah, absolutely. The thing about temperature you have to remember is it is an average, so things are going on at different temperatures.
It was an amazing episode of a David Attenborough programme where they were looking at life in the Antarctic, and they show this very, very cold water coming down from the surface and then hitting the floor of the ocean, and it just comes down and freezes in like a stalactite going down, hitting the ocean floor and then spreading as a sheet of frozen water along the bottom, because once it had enough ice there to start the freezing process, that then kick-started the formation of a whole crystal, and that whole nucleation process kicked in.
So that's something called supercooled water, which you can see, and it's really cool. If you get if you get water and leave it to stand, it can get colder than the freezing point without actually freezing. If you then pour it out, it'll freeze in amazing structures.
Thanks, Laura. And thank you, Pinchas, for a very good question.
Is water unique?
I wouldn't like to say definitely unique, because there can always, but it's one of those really, really weird substances. You get different types of ice, so in different temperatures and pressures, ice can form different crystals, and there's all sorts of odd things that it can do.
It's certainly very unusual amongst the kind of everyday things you'd see. So if you had some oil and you froze that, oil ice would actually sink in oil. Now, we all think that would be really weird, but actually solids should be denser than liquids, so they should sink. We're just so used to water that we think ice floating is normal, whereas actually it's really quite strange.
Isn't there, Dominic, on some other planets, I mean, the people have said on Titan, Saturn's biggest moon, the pebbles that are made from the hydrocarbons that freeze on Titan would sink. They wouldn't float like the kind of ice that you get in the oceans here on Earth.
That's absolutely true. These moons of planets like Saturn, they have not water oceans, but oceans made of hydrocarbons, these materials like petrol, and they behave in the way that most materials do. Their solid forms are more dense and they sink as compared to ice that floats.
Thanks, Dominic, and thanks for a brilliant question as well, Pinchas. That's great to have you on the programme. You're listening to a special question and answer edition of The Naked Scientists, with me, Chris Smith, as well as Laura Howes, Dominic Ford, Ginny Smith and Dave Ansell. If you'd like to send any questions, you can do so to chris@thenakedscientists.com. You can follow us on Twitter @NakedScientists, or you can look us up on Facebook, facebook.com/TheNakedScientists. Now, we've also got an experiment for you to have a go at, or even if it's a thought experiment, if you don't fancy having a go at this one. Dave, what do you want people to try and do?
So basically, it's sort of a challenge, and when you know how to do it, it's a great way to confuse your mates. Work out how you can empty a bottle without damaging the bottle anyway, just by turning it upside down, how to empty it as quickly as possible. So if you've got any ideas,
squeeze.
How to pretend the bottle is made out of glass, you're not allowed to squeeze it. All you can do is move the
Smash
bottle around.
Smash it with a hammer if it's made of glass. That would empty it pretty quick.
It would certainly empty it very quick, though it would be less interesting scientifically.
Okay, so have a go or have a think about it and tell us how you think you would empty a bottle just by inverting it as fast as possible. Dave has brought in some apparatus, so you're going to do this towards the end of the show.
Yes, hopefully the expensive electronics will survive the experience.
Brilliant. Thank you very much, Dave. Now, Ginny, Adrian has got a question for you. Adrian, what's your question?
I've got a Tissot watch, a wrist watch. I've got that now for about 51 years. It's a gold-plated thing. Beautiful run, but it's automatic. No batteries. You don't wind the thing by any movement of your arm. It winds itself up automatically. Now, I've been intrigued for many years that if I'm slightly off color, say a slight temperature or a flu coming up, that thing stops. The only time I take it off is when I go to swim or in the shower, but when I'm a bit off color, it stops. What could be the reason?
Ginny, what do you think?
Automatic wristwatches are really, really clever. So you used to have to wind a watch because a watch needs energy in order to move the hands around. So you used to have to wind up a little rotor inside that then drives the hands around. But what these kind of automatic watches have is there's a weighted bit inside that moves every time you move your arm. And you move your arm quite a lot during the day without even noticing it. So that movement winds the spring that drives the hands. Watches vary in how much energy they can store. Most of them actually you can take off overnight, or even if you leave them on, you're not moving overnight, and they'll store enough energy to still work perfectly well the next day. So the only thing I can think here is that if you've been ill, you're probably not moving around as much. If you've got flu, you might be, taking it a bit easy on the sofa. So even if your watch is on, chances are you're not moving your arms around quite as much. So maybe if you're ill for a day, then it's gone a night and a day and another night without much winding. That might be enough for it to stop.
So there you go. It's all down to not being sufficiently active to keep the watch around. So keep yourself well, Adrian. This is The Naked Scientists with Chris Smith, Dominic Ford, Laura Howes, Ginny Smith and Dave Ansell. It's a question and answer special, and that means you can email in and you can ask us any question on anything. The email address chris@thenakedscientists.com. You can also tweet @nakedscientists, or we have a Facebook page running as well. You go to facebook.com/thenakedscientists and we'll pick those messages up. Right now, Les is in over. Hello, Les.
Hello.
Fire away.
After going for several months without it, tinnitus has started today, and what's made me wonder is what is the actual noise, and is there any, I know there's no cure for it, but what actually causes the noises?
It's distracting, isn't it? Yes. Well, the definition of tinnitus, I hope not in response to this programme, Les, of course, but the definition of tinnitus is when you have a sound experience in your ears or ear in the absence of any external presentation of sound. So in other words, you're hearing something that you know is not there. It's coming from inside your ear. And there's a number of reasons why this can happen. The commonest is because of the ageing process and damage to your ears caused by degeneration of what are called hair cells, and inside your inner ear are cells called hair cells that have tiny hairs projecting off of the cell, and when vibrations from a membrane inside your ear are transmitted into those hairs, they make the hair cells fire off electrical impulses, and they send the electrical impulses via a nerve to the brainstem and then on to the main part of your brain that does the hearing. If you are exposed to very loud sounds chronically, in other words, over long periods of time, we don't exactly know why, but it does damage these cells and eventually they begin to be lost. And this means that the sounds that they would have picked up and sent on to the brain no longer get transmitted to the brain. And it's a bit like if you're listening to the radio and you can't quite hear it loudly enough, you turn up the volume. And that means that you don't only amplify the noises you do want, you also end up amplifying the hiss that you don't want. And so we kind of regard tinnitus as a sort of hissing noise, which is brought about by the brain increasing the amplitude or gain in the system in order to try to make sense of the sounds that seem to now be missing. There are other things that can also cause tinnitus as well, and one of them is probably infection. We know that some viruses can make a beeline into your inner ear and can irritate the nerves. In fact, there's been some viruses going around in the last few weeks called enteroviruses that can get into the nervous system, and they tend to cause things like headaches and pain behind your eyes. Occasionally you know you've got one because you can get ulcers in your mouth as well. And they can sometimes also cause this tinnitus sensation. And also don't forget drugs as well, because there are certain drugs and medicines that can cause irritation of the cochlea, the hearing organ, and they include aspirin. If you take lots of aspirin, you can get ringing in your ears, or a drug like aspirin called salicylic acid, and also some antibiotics can also do this as well.
Are those kinds of tinnitus reversible? So if you take lots of aspirin, do you get it for a while and then it goes away again, or were you stuck with it for life?
It depends. If you take a lot of aspirin or salicylic acid, which is a chemical relative of aspirin, the stuff that's in willow bark, that tends to go away when the drug flushes out of your system. If you take certain antibiotics, and this includes the antibiotic gentamicin, which is sometimes given for certain deep-rooted infections in the body, that is very toxic to the cochlear hair cells, and if it damages them, it can sometimes cause tinnitus and ringing in the ear that unfortunately ends up being permanent. Let's go to Rob, who is on the phone. Hello, Rob.
Hi there, Chris.
You've got a question for us about immersion heaters.
One often hears that switching off a heater at night, for instance, for a few hours, will create massive savings of electricity and thereby cost. And I'm just not understanding that. A reasonable geyser will stop any heat loss. You'll get a very small heat loss, but you're not going to save huge amounts of money. Or have I got that all wrong?
Let's ask Dave, and Dominic are our resident physicists. So should you leave the immersion heater on all the time, or is it better to turn it off and only turn it on when you want it, Dave?
So essentially with something like a hot water tank, the hotter it is, the more energy it's going to be losing. So if it's not very well insulated, the effect is even bigger. Essentially, if you keep it hot all the time, then you'll be losing lots of electricity, lots of energy, so you're going to have to put more electricity in there to keep it hot. If you turn off the electricity, it will cool down, and the more it cools down, the less heat it will lose. Now, almost the best solution would be to improve your insulation, but if you can't do that, or that's expensive or difficult, turning it off will save energy. I couldn't say off the top of my head how much it's actually going to lose.
It's interesting if you look at the typical electricity usage of a house. I think heating is one of the really big costs you tend to have, and that's water heating but also space heating. You know, if you look at an airing cupboard where you've got a hot water tank in there and you feel it, it feels hot, so that heat is leaking out of that tank into your house. So if you've got that on all night, then you're basically heating your house with your hot water tank all night.
Jolly nice. Could be useful in my house. It's freezing in wintertime. You're listening to a special question and answer edition of The Naked Scientists with me, Chris Smith, as well as Laura Howes, Dominic Ford, Ginny Smith and Dave Ansell. If you'd like to send any questions, you can do so to chris@thenakedscientists.com. You can follow us on Twitter @nakedscientists, or you can look us up on Facebook, facebook.com/thenakedscientists. Laura, here's one for you. Ali says, can magnets on pipes soften water? I'm really intrigued to know the answer to this. What do you think? You can see these gadgets, you buy them in magazines and things. Stick this on your water main, it'll stop your pipes flaring up. True or false?
I have to say I'm pretty unconvinced by these claims. I have sort of looked at it. I've tried to work out what the magnets could be doing. We have to think about what hard water is. It's mainly calcium and other minerals dissolved. There is a tiny amount of iron in there that could be affected by the magnets, but I just can't quite see what could be happening there.
And even the iron is in a form which is actually magnetic.
Yeah, so most of it's in an unmagnetic form, so it's in one of the electronic configurations that isn't actually magnetically sort of active.
So we're giving that one the
We're giving that one the water filters and things, I think, instead.
There's probably an element of placebo effect here, in that if you've bought a gadget and you've put it on your pipes and you drink the water...
Placebos for pipes.
It probably does taste different to you. Or you possibly think, oh, yes, my kettle's not firing up as quickly as it used to, but it's likely to just be the placebo effect that you think because you've done something, something's going to happen.
But equally, you're hardly likely to cut into the water main just to have a look and see if it's furred up, are you? So I think it's very likely that most people just go, oh, I assume it's working. It's sort of, as you say, you sort of feel happy about it because you think you've done something, when in fact, actually haven't probably done anything. So the conclusion of the panel here, everybody, if I speak for you by saying, you're saying don't waste your money, would that be a reasonable summary?
I'd say pretty much, yeah.
Okay. We have got Dave, who's on the phone in St Ives, with a question, I guess probably for Dominic. Hello, Dave.
Oh, hiya. My question is, when an aircraft takes off against the spin of the Earth, does the flight take longer? And vice versa, when it takes off, it goes with the spin of the Earth, does the flight take less time?
Well, in fact, what's important is the plane's speed relative to the Earth's atmosphere, the air around it, because that's what's giving it its lift up into the air, and that is what's providing the friction, which is meaning it's having to thrust to keep going forwards. And the Earth's atmosphere is rotating with the surface of the Earth below it. The reason is because it's got friction with the land masses beneath it, and that means the air is always being pulled to rotate with the Earth. So, in fact, because the air above us is rotating at the same speed as the land below, and what matters is your airspeed, your speed relative to the air, it doesn't matter whether you're going with or against the rotation of the Earth. Dave?
The one thing I would say with that is that there are some latitudes where the wind tends to blow in one direction. So in our latitude, the prevailing winds are from the west, and they get even faster as you go higher up. So it's a lot quicker to fly from the States to here than from us back to the States. So it's actually quicker to go against the direction of the spin of the Earth than with it. It just happens to be the way the air is moving. In other places, the wind moves in the opposite direction, so you have the opposite effect.
And I guess the other thing to say is that if you're going above the Earth's atmosphere into space, then satellites all do go from east to west, because there you're above the Earth's atmosphere, you haven't got this drag from the air anymore, and it is a lot easier to get into an orbit that goes with the Earth's rotation rather than against it.
A little bit of drag, though, isn't there? Because the International Space Station and some of the lower flying satellites have to be boosted every so often because they are experiencing a little tiny bit of drag from the wisps of atmosphere out there.
That's right. The International Space Station is in quite a low orbit at about 130 or so kilometres up, and it does have to thrust about once a month to maintain altitude.
Dominic, thanks. Dave, I hope that clears that one up for you.
Yeah, it's interesting. Thanks for answering that one. Cheers.
You're welcome. Thank you for joining us on the programme.
Thank you.
This is The Naked Scientist. Chris Smith, Dave Ansell, Ginny Smith, Laura Howes, Dominic Ford. I'm getting faster answering your science questions. We've got two things to challenge you with. One of them is I asked you at the beginning of the programme, how can you throw something as hard as you can and have it come back to you, even if it doesn't hit anything, there's nothing attached to it, and no one else catches it? Any solutions? Let us know. Dave also has a challenge for you, which he's going to do the experiment. It's not a trick at the end of the programme. Remind everyone what you want them to do, Dave.
So basically, what's the quickest way you can empty a bottle without damaging the bottle itself? So you've got a bottle of water, how do you empty it as quickly as possible?
Thanks, Dave. Have a go. Nina's on the phone for you, Jenny. Hello, Nina.
Hello.
Fire away.
I want to know that why do I sometimes feel like I already know what's going to happen next?
So déjà vu is a really common experience, but scientists really don't understand what causes it. And the main reason for that is that it's very hard to predict when someone's going to have a déjà vu experience or to induce them. So what we would love is to get someone in an MRI machine having déjà vu and look at what's going on in their brain. But it's really, really difficult to do. Some researchers at Colorado State University recently actually did manage to provoke déjà vu using a kind of immersive visual technology, sort of 3D
like
thing.
Virtual reality.
Yeah, sort of virtual reality thing, but very immersive. And they showed them various scenes. And they found that déjà vu was provoked most regularly when the layout of a scene was similar to one they'd seen previously. So the participants knew that the scene was new because they knew that they were only going to see each scene once. So they had that feeling of, I can't recognise this scene because I haven't seen it before. But because the layout was similar, they got that déjà vu experience. So that suggests that it might be that you get it when you've seen elements of a scene before, when there's something familiar about it, but you can't quite place where that familiarity is coming from. And you know that the scene is new, that you shouldn't recognise it. And that's what gives you the weird feeling of déjà vu.
I once had a bike accident and hit my head rather hard. And for a while after that, I got this kind of, I've met this person before. So I'd meet someone at a party or something. And then after about 50 minutes, I was sure I'd met them ages ago. But that kind of, I wasn't sure whether it was Cambridge, and I probably had met them ages ago because Cambridge is a very small town, or whether there was something like my memory wasn't quite working properly, and there was some effect like that.
Well, we actually know a bit about what area of the brain's involved because some people who have epilepsy get déjà vu as part of their symptoms. And that happens when you get epilepsy that occurs in your temporal lobe, which is the bit sort of just above the ear. So it could be that if you had a bit of damage going on there because you'd hit your head, that might make you more likely to have these feelings.
Has anyone else ever had déjà vu?
I think I have it with childhood memories sometimes, things that I don't remember perfectly. And I think, why do I feel slightly familiar in this place? And I think that's, when I was 5, maybe I was here.
It happens to me when I get sleep deprived. And that, I think, is interesting because also sleep deprivation does trigger brain patterns of activity that we know also trigger epilepsy in people who are epileptic. So it's interesting that you said epileptics get it, but also sleep debt can do it, Jenny.
Yeah, they've done quite a lot of sort of retrospective studies where they ask people, when do you get déjà vu, how often do you get it? So they found that people do get it more often when they're tired and also when they're stressed. But there were some other interesting things, like it's more common in young people and it's more common in well-educated people, which doesn't really seem to make that much sense. But also people who travel a lot, which you can kind of understand a bit more because you're more likely to go to places that are new. And of course, you can only actually have déjà vu in a place that's new. You can't have it in your home because you know you've already been there, you know why it's familiar. So that one kind of makes sense, but I can't get my head around why it's young, well-educated people who seem to get it more.
Thank you, Ginny. You're listening to a special question and answer edition of The Naked Scientists with me, Chris Smith, as well as Laura Howes, Dominic Ford, Ginny Smith and Dave Ansell. If you'd like to send any questions, you can do so to chris@thenakedscientists.com. You can follow us on Twitter @NakedScientists, or you can look us up on Facebook, facebook.com/TheNakedScientists. Dominic, one for you, Robert in Cambridge. He says he's actually busy milking his goats, so he can't come on the programme. But he wants to know, and I'm not sure what the connection is between goat milking and this question, but he wants to know, how do they process body waste in space?
I certainly didn't know there were any goat farms in Cambridge, but you learn something every day.
Or in space.
Or in space, yes. Body waste in space. Well, in fact, a lot of it you ship back to the Earth now.
Ship with a P, yeah.
With a P, that's right, yes. If you're on the International Space Station, then you have these what are called Progress spacecraft that come every month or so and they deliver new supplies, food, etc. And then once you've taken the food off those, you basically put the body waste back in there and then you send it back to the Earth. Things like water, you don't really want to be transporting large masses of water around. So there is actually a process on the space station where you take the wee from the astronauts and you can extract drinking water from that. And then the other constituents of that pee you just put back in that spacecraft and send back to Earth. Historically, back in the Apollo era, you would just throw it overboard, basically, and you would have these ice crystals of human waste flying off the side of these Apollo spacecraft. But the reason why you don't do that anymore is because those ice crystals are moving incredibly quickly, and if they collide with other satellites, they can be very damaging and they can smash a very expensive spacecraft.
That would be rather ironic, wouldn't it, to be taken out by a blob of human excrement if you're a very expensive satellite or whatever.
Ironic, but in fact still a threat today because, some of this stuff is still there from 40 years ago and it's still just whizzing around in orbit around the Earth.
Dominic, thank you very much. We're coming to Roy, who's in Spalding, in just a second. Before that, though, Laura, Naresh wants to know, will some silver jewellery harm my health? Is silver jewellery all right?
I would have thought mainly silver jewellery would be fine. First of all, because silver's fairly unreactive. And secondly, we've been wearing silver jewellery for many, many years. You can find it in archaeological sites all over the place. I think there would be potentially a little bit of a worry if there's something that he's allergic to in the alloy, because no silver is 100% pure usually when you're wearing silver jewellery. So that can be a problem. And some of the silver atoms will eventually, if you're wearing a ring, some of those atoms will move into your skin. But I wouldn't have thought there'd be any kind of problem.
There was a gentleman, I think we discussed him here on the programme previously, who thought that silver was a good thing because it kills microorganisms and that kind of thing. So he was drinking a solution of silver salts every day, and he unfortunately went blue. And this is a condition called argyria, and he looks like a Smurf. Honestly, he's bright blue, and it's permanent because the silver goes into the skin and then reacts with sunlight, and you get this bluey-grey gunmetal sort of coloration. And I've seen him on television, he's absolutely blue.
He is absolutely blue, and what's even more astonishing is that he still drinks the colloidal silver because he still believes that it gives him these health-giving properties. But I think there's a big, big difference between drinking what we call colloidal silver, which is a large amount of it, and getting it into your skin where it reacts, and a couple of atoms occasionally getting into your skin. I mean, you eat probably more than you'll absorb from your jewellery.
So, Naresh, do not eat your jewellery. Roy's in Spalding. Hello, Roy.
Good evening.
Fire away.
The American engineers have just developed a camera which, by what I've seen on television, actually slows light down. The pictures I've seen on television is an object that looks like a plastic drinks bottle, and they project a light beam into one end, and it turns into a globule, and it moves very slowly. I was wondering if you could possibly tell me of what significance it's going to be to them, whether they're going to use it in spacecraft that go out on exploration into space or use it on telescopes.
Okay, so the way that camera works, I saw this story a while ago. It's an absolutely incredible thing. I think it's brilliant. Is that essentially it actually can only take one line of the picture. So a picture's made up of lots of different lines. You can only take one line of a picture in each burst of light. But basically, they send out lots and lots of bursts of light very, very quickly, and they build up lots and lots of lines. And you take them exactly the same position of where the burst of light is, so you can build up the video that you've seen. The way they want to use it is because the really neat thing is if you can actually see light as it's travelling, is that you can sort of use it a bit like radar on a really small scale. So you can actually bounce it off a kind of normal wall, and the light will bounce off the wall, then bounce around the room, which you can't actually see, and then bounce back again. And if you can see exactly when all that light gets to you, then if you can put that through a big computer, you can actually work out what's round the corner. So you can actually see round a completely normal corner with no mirror at all, just by being able to see the light as it comes back 1 nanosecond at a time.
So what you're saying is if you see a pulse of light arrive at a certain time, you know that light must have travelled a certain distance, you know the speed of light, so you know something in that room round that corner bounced that light back at such and such time, so it must have been exactly such and such distance away.
And you've got some idea where it's coming from, so you can take all this information, put it together and build a model of a room.
Would you be able to tell what was in the room, or would you just know that there was something?
Pictures I've seen, it's quite early days.
It's amazing, isn't it, when you see it?
They've actually kind of built up a rough shape of an object, and you can get some idea of the colour as well. If you've got a colour camera, you can tell what colour of the light was which you got there.
It was one of those mannequins, those artists' wooden mannequins, you know, the ones you put into funny postures, and they had one of those. And the pictures that it rendered afterwards were absolutely stunning. You could tell without a shadow of a doubt what it was, couldn't you?
Yeah.
Which was absolutely stunning. There you go, Roy. Hopefully you heard your question totally dissected and pulled to pieces and answered thoroughly for you.
Thank you ever so much, gentlemen. Yes, you've shed a great deal of light on it, because I was wondering, you know, as you've just said, of what they were going to actually use it for. But I'm very grateful to you for answering my question. Thank you very much.
We're very grateful to you for phoning into the programme. Thank you, Roy and Spalding. It's The Naked Scientists, Chris, Dave, Ginny, Laura and Dominic. We're answering your science questions and encouraging you to do kitchen science experiments. Dave, remind people what you need them to do. We've had Les has speculated, and he's actually on the right lines for the answer, because I know the answer to this. But Les, you're on the right lines. What do you want people to do? What's the answer you're after?
So basically, how to empty a bottle as quickly as possible. So you've got a bottle of water, you can't tamper with the bottle, you can't squeeze the bottle, you can't smash the bottle, all of which Chris has suggested, by the way.
Damn. None of my suggestions.
How can you empty it as fast as you can?
Cameron has a question for us. Hello, Cameron.
Hello.
What would you like to know?
I would like to know when an airplane does a vertical wings test, like when the wings are perpendicular to the horizon, like during an air show or something, where does the vertical component of lift come from to keep the plane in the air?
So the plane's basically flying on its side. The wings can't be doing anything because they're vertical. So the lift must be coming from somewhere else. Normally when you watch them doing it, they're actually at quite a big angle. So they're not flying horizontally, they're sort of flying at 20 or 30 degrees to the vertical. And so you'll be getting some lift from the side of the body of the plane, from the side of the fuselage, some from the tailplane itself will be giving you some lift. And most of the kind of planes which do this have got very, very large propellers which can throw an awful lot of air backwards. So because the plane's pointing upwards, that air is being thrown downwards. And so you get an equal opposite reaction and the plane gets pushed upwards.
Thanks, Dave. Similar sort of thing when planes fly upside down and people say, well, if the wings are generating lift in the right way up position, why should the plane be able to fly upside down? It's just that very high angle of attack, isn't it?
Yeah, wings are optimised to fly the right way up normally, unless you've got a really stumped plane. But if you fly them upside down, and as long as they've got enough angle of attack and you push them through the air hard enough, you will get enough lift to stay up.
Dave, thanks. You're listening to a special question and answer edition of The Naked Scientists with me, Chris Smith, as well as Laura Howes, Dominic Ford, Ginny Smith and Dave Ansell. If you'd like to send any questions, you can do so to chris@thenakedscientists.com. You can follow us on Twitter @NakedScientists, or you can look us up on Facebook, facebook.com/TheNakedScientists. Vincent's in March. We'll be coming to him shortly, but first, This is for you, Laura. Rob Waite wants to know what chemicals come leaking out of batteries. He said he was doing some things at Christmas time which made him think of this, and put some batteries into a toy that he had left over from the year before. And there was this leaky stuff and white powder all over the contacts of the batteries. What's actually happening when this occurs?
Okay, so what's actually happening here is the electrolyte from the battery is leaking out. So you think of batteries, it's sort of school-level chemistry, but you've got a reaction going on between two metals, and there's some sort of electrolyte in the middle that's allowing charge to be transferred between these two sides of the battery. And that usually in sort of your normal alkali batteries is potassium hydroxide usually, or something like that. Eventually, though, your batteries do keep reacting even if you've not connected them up. They react very slowly, but they do leach a little bit, and there can be side reactions, and eventually these things can just sort of pop open, at which point your electrolyte comes out.
Is it nasty?
Potassium hydroxide is not very nice. It is an alkali and it's quite caustic. However, it then reacts with carbon dioxide in the atmosphere. So actually what you're seeing is those white crystals. That's actually potassium carbonate, and that's actually potash. That's the main component in
That's
potash.
good for the garden.
So, I wouldn't suggest necessarily
Bury
knocking
the
it off
battery.
and putting it in your vegetable patch or anything. But probably don't start licking your batteries or anything like that, but just dispose of them. And if there's any on your contacts or things, you can start trying to wipe that off, potentially with lemon juice or something.
And I guess even if it's potash on the surface, underneath you've still got the potassium hydroxide, so you don't really want to knock that surface off.
No, quite. So why you might want to use something like a weak acid to try and neutralise it as you're washing it off. The other thing, of course, is that these things can start creeping in to electronics, and so you can actually, if you've left your batteries in something for long enough, you can start really messing around with your circuits and degrading them.
Lovely. Laura, thank you very much. We haven't forgotten about you, Vincent, in March. We're coming to you to talk mirrors in just a second. But first, Yusuf wants to ask you a question about dehydrating in a bath, Ginny. Hello, Ahmed, sorry.
Ahmed, yes. Hi.
Hello.
I have a question about water consumption and dehydration. I know you're not supposed to go without consuming water for 3 or 4 days, but I was wondering if a person would be, say, submerged in a bath or in some kind of, fresh water, would that stop that person from dehydrating and needing to consume water?
The short answer is no. Your skin is pretty waterproof. That's why we can go out in the rain and we don't get all soggy. Well, our clothes might, but our skin's actually pretty waterproof. Although if you were in somewhere very, very hot, sitting in water might actually help stop you from dehydrating, just because it would keep you cool so you'd sweat less, but you wouldn't actually be able to absorb it through your skin. Now, there was a group of researchers in Denmark who actually decided to test this, but rather than using water, they thought it would be a bit more fun to do it with vodka. So they sat with their feet in a bath of vodka for a while, and they tested their blood alcohol levels, and they found that they didn't get drunk at all. So that just shows that you're not absorbing things through your skin like that.
We did interview them on this programme, Ginny, and they did say that although they didn't absorb any alcohol according to the blood test, they did all start talking very loudly and telling rather raucous jokes. So it had a psychological effect, if not a physiological one.
Well, I wouldn't have been surprised if they'd inhaled some alcohol fumes and got drunk that way. I'd be quite interested to know, though, if their feet went wrinkly, because we all know that our fingers and toes go wrinkly in the bath, and people used to think that that was because you were absorbing water through your skin. But actually, some recent research at Newcastle suggests that it's evolved to help us grip objects when our hands are wet. And they think it's actually down to your nerves, because if you've got nerve damage, it doesn't happen. So they found that people were much better at picking up marbles underwater when their hands had been in water for a while, so their fingers had gone wrinkly. So it works a bit like the tread on tyres, but it's actually controlled by your nerves, not by you absorbing water through your skin.
So there you are, Ahmed. You wouldn't be able to survive the dehydration, but you would nonetheless be able to pick things up beside the bath very, very well.
Very useful.
Great to have you on the show. Thanks for calling in.
Thank you very much.
Let's go to Vincent, who's been waiting patiently. He's in March. Hello, Vincent.
Hello, good evening.
What would you like to talk about?
Yeah, my question is, if you could make a perfectly spherical mirror with the mirror on the inside and somehow fire a photon of light into it, would it glow forever?
Dominic?
So you've got a perfectly spherical mirror, you've got a photon in the middle of this. I guess whatever direction that photon goes in, it will always hit the mirror and bounce off. The problem's going to be making this 100% reflective mirror, because any mirror that you make, it's got some small percentage chance of any light, rather than bouncing off that mirror, will hit a piece of dirt or just get absorbed as heat into that mirror. for a piece of aluminium foil, about 70% of the light that hits that is reflected, and if you make a really high-class astronomical telescope mirror, you can get up to about 99% chance. But of course, this photon's bouncing around at the speed of light. It's bouncing off so many times that eventually it's going to get absorbed and just turn into heat.
So is that a no?
I think that's a no. I think yes.
Could I just ask one thing? If you could somehow associate this with the sort of solar panels and all that sort of thing, could it potentially provide energy forever?
Well, of course, unfortunately, to get energy out of sunlight, the solar panel has to absorb that sunlight and turn it into electrical energy. So in practice, in the process of absorbing that energy, that light is then destroyed. You can't use it again.
We also want solar panels that are as least reflective, that's very bad English, but you know what I mean, as unreflective as possible so that they absorb as much energy and give away as much back out. That's why they're black, isn't it?
Yeah, you want them black, absorbing everything that hits them.
Dominic, thanks. You're listening to The Naked Scientists with Chris Smith, Dave Ansell, Ginny Smith, Laura Howes and Dominic Ford. We're within 10 minutes of the end of the programme, so now is your chance. If you are burning to ask something scientific, email chris@thenakedscientist.com, tweet @nakedscientists, or you can find us on our Facebook page. In a second, Dave is primed with his bottle of water to do this experiment. He's been saying to you, how do I empty all of the water out of this plastic bottle of squash, as it was, without actually having to break it, squeeze it, or cheat in any other way? What's the fastest way to get the water out? We'll find out in just a second. First, let's talk to Connor, who has a question. He's in Tillingham. Hello, Connor.
Oh, hello. Oh, yes, my question is, one night when my wife and I were getting ready to go to bed and we turned off the light, I closed my eyes and suddenly I saw an image. Well, I think actually it must have been an old-fashioned bakery because the wall was floor to ceiling with cast iron ovens. It gave me a bit of a shock, and I opened my eyes and I told my wife, and she said, "Can you see anything else?" So I closed my eyes again. The wall with the ovens were back. I turned my head to the left and I could see another wall with other cooking instruments. I opened my eyes and I told my wife and everything. I got a bit concerned actually because it took about an hour eventually before I could close my eyes and just go to sleep. My question is this anything to do with my memory?
You didn't see any winning lottery numbers coming up by any chance, did you?
No.
Oh, okay. Just thought I'd ask, just in case. Well, this is actually a sort of hallucination which is caused by often putting people into the dark. And Ginny can probably comment on this in a second, but there are these things which are called float chambers, and you put people in these experiences on purpose sometimes to do research studies. You effectively put someone in a very quiet, very calm, dark environment. It's a sensory deprivation experience, and this has the effect of triggering all kinds of strange hallucinations. They do it with medical students sometimes in psychology studies, and people will say, I can hear voices, I'm convinced a telephone is ringing, I'm seeing things, and it's probably because, in the same way as we were discussing earlier, when you have tinnitus, this is the hearing part of the brain failing to get a signal from the ear's cochlea. So it turns up or amplifies the signal a bit, and up comes the noise, the hiss, which is what you end up hearing as tinnitus. It seems like when you deprive the visual system of inputs and other parts of the brain, they start to invent signals or increase the amplitude of signals that are already there at low level, and it makes them manifest a very real experience. Would you go along with that, Ginny?
Yeah, I think that sounds right. I mean, our brains are quite incredible things and we don't fully understand them yet. But one of the things we think is that we actually store more memories than we know we do. And actually, when we forget things, it's not that the information isn't there anymore. It's often just that we are unable to access it. So it may be that this was a memory that you don't even know that you have, but that's there. And because it was dark and it was quiet, it came back to you.
Exactly. And so it was sort of playing out in the visual system just because that part of the brain is already sort of seeing that experience.
I guess the other effect is certainly I get sometimes as I go to sleep, I start seeing sort of random images. And if you're kind of getting to bed and turn the lights out, that might be something related to sort of starting to dream while still being awake.
That's certainly true. It could be sort of that weird phase between being awake and being asleep. And you do have rather strange experiences. They're called hypnagogic experiences, aren't they?
Yeah, there are even some people who can have lucid dreams where you can sort of control your dreaming and it's almost like you're awake, but you're dreaming, but you're asleep. And we don't fully understand how they do it, but it could be something along those lines.
There you go, Connor. Those are our speculations. I hope they put your mind at rest. I think you're completely normal, though. It seems like all of us lot in this room, everyone's nodding their heads, has had a similar sort of experience. Right, Dave, tell us, how do we do this? How do we get this water out of this bottle?
I guess the most sort of obvious way of emptying a bottle, if as Ginny can demonstrate, is just opening the lid and turning it upside down.
Okay, so Dave's given me a bottle here, which is exactly the same as his, so I'm going to open the lid and turn it upside down now.
Yeah, and I will try and count how long it takes.
Okay, we're going to see how long this takes.
Right the way upside down.
Ooh.
Took about 7-8 seconds.
7 or 8 seconds. Okay, so you'll notice with that, the thing which seemed to be slowing it down a lot was getting the air into the bottle. So in order to empty a bottle, you've got to get the water out. In order to get the water out, you've got to get the air back in. And the only way it could do that is kind of by glugging. So it's got to let a bubble of air up, which stops the water coming out, which slows everything down. So in order to speed the water coming out, you want to somehow separate the water from the air. One way of doing this would be to knock a hole in the bottom of the bottle, but that's kind of cheating. Another way, if you were very cunning, would be to put a straw in or something like that, which is sometimes done. But I'm going to do something a little bit more elegant, which is spin the bottle.
Oh, wow. 4 seconds.
So that was much quicker.
So you span it, just like to make a spiral, like a vortex.
So there was almost like a little tornado in there. So the water was being thrown out to the sides, which means that there was a gap in the middle which the air could get up through. So the water could go down, even though sort of spinning around the outside ought to slow it down a bit. It sped up so much by letting the air up in a very smooth, convenient way up the middle that it completely overwhelms that effect. And it's far quicker than just turning it upside down.
It's also neater. I noticed you didn't splash any on yourself
yes,
like
I was
did.
less worried for the equipment during the Dave attempt. Do we see the same sort of thing being used in the real world? I mean, it's very nice us doing this here, sitting in this room, but do you see the same sort of science manifest in nature or actually industrially?
Certainly, in the centre of a hurricane, you end up with, so most of a hurricane, you get air going upwards and spinning very quickly. In the middle, you get a kind of dead area where air is actually going down, which kind of feeds the circulation. And certainly, whenever you're emptying a big tank, you want to open a valve at the other end so the air can get in, so the fluid can get out.
There was one trick that people used to do at school to drink a can of drink very fast, which was, I think, sort of what you were saying, which is that you punch a hole in the bottom of the can, then you pull the ring pull off and put the hole to your mouth, and the can just empties under gravity very quickly. Is that going to be faster than the spin trick?
It should be slightly faster. If the hole's very large, you've essentially got more of the bottom of the aperture at the bottom of the bottle open, so the water's got more space to flow through, so it ought to go quicker.
Dave, thank you very much. And if you want to have a look at that experiment, Dave's done a write-up for it. It's on our website at nakedscientist.com/kitchen science, along with about 250 other experiments that are there for you to have a look at. Thanks very much, Dave. Dominic, okay, horrible question for you to answer in 1 minute. In fact, you've got less than 1 minute, Dominic, because I keep rabbiting. Mark Faison asks, why do mirrors reverse but not invert things?
Well, in fact, it's a bit of a myth that mirrors reverse things, because if you're looking in the mirror, you wave your left hand, you look in the mirror, the waving hand is actually on the left. It's exactly the right side it should be. But if, let's say, I'm looking at Drinny, and if I was sitting behind Drinny in a car, and we stuck out our left hand or right hand, we'd agree as to which side was which. But of course, to face me, Ginny's sitting on a swivel chair, she's turning around to see me. She's inverted her sense of left and right when she's turned round to look at me. Now, the way that Ginny could turn round to face me would be to stand on her head. She's now trying to do that in the studio. I'm not sure that's going to end well. But, of course, rather than inverting her sense of left and right, she's then inverted her sense of up and down. So the inversion is, in fact, when Ginny turns around to look at me, rather than when I look in the mirror.
And so the answer is?
The answer is that nothing is actually inverted when you look in the mirror, but things are inverted when we face each other in the studio.
Dominic, thank you very much. So it's basically one giant con, isn't it?
Basically, yes.
Well, that is it for this week. Thank you very much to our contributors, Dominic Ford, Laura Howes, Ginny Smith and Dave Ansell. The Naked Scientist comes to you from Cambridge University. It's supported by the Wellcome Trust and the EPSRC. I'm Chris Smith, and thank you very much for listening. Goodbye.